Hello everyone, I'm Guanhua. Today I'm going to introduce you my project, the performance comparison between the two variants of recurrent neural networks, transformer and extreme gradient boosting, the XGBoost, on blood supply dataset. Before we start the technical part, I want to introduce a fact that we are facing a serious shortage on blood storage. And blood waste is also a serious problem at the same time. We know blood cannot be manufactured artificially, so that is why you may always see a notice. You may always see a notice like that. The emergency all blood types needed. We are rarely facing blood shortage nationwide or even worldwide. So I was thinking maybe it is time for us to do something to help to solve the serious shortage. The prediction tools we learned are absolutely helpful to the blood field. The models and algorithms could help the blood center make strategies on blood storage and reduce blood waste. I believe saving more blood is equal to saving more lives. So in the project, I used two types of recurrent neural networks, LSTM and GRU, and then used the transformer and then XGBoost. Let's take a look how the blood data look like. The data is in time series format. The original data set recorded different blood products. We have red blood cells, plasma, blood platelets, and cryo. Each of the blood products are also divided into 4 blood types, A, B, O, and AB. Also include a total amount of 4 types of blood. Each data point was recorded every day from 2014 to 2020. In the project, because there are missing values in platelet and cryo, so I only use part of the data for training. I use 2 most common blood products, the red blood cells and plasma, and only keep the total amount of 4 types of blood from 2014 to 2020. So 80% of the data was split into training set and the rest 20% was used as testing set. For each part of the whole data set, I construct the window features and set the window length with 7. I also construct a feature that contains previous 7 days data and the label is today's data. So in other words, my model used data from previous 7 days to predict today's data. And the time series format data was converted actually to a supervised learning problem. So however, one challenge is that the amount of red blood cells and plasma both have a very large range. So for example, we could see from the graph, the data are all mainly hanging between 100 and 800 units. So one way that I use is the min-max scaler to solve this problem. All data was scaled within 0 and 1. After the prediction, I use the inverse transform function to convert the prediction results back to its original scale. Okay, now let's focus on the models. So 4 models were used for comparison, 3 deep learning models and 1 shallow model XGBoost. So to make the comparison fair, I used the same input for each model. So during the training, I found some tricks when setting the time step. It usually related to the seasonality. So I could try to set the time step to a week or a month. Here I found using the time step equals to 7 has a better result than others, and the epochs is equals to 10 for each model. I also used the item as the optimizer of loss function MSE for all models. And item is a modified version of stochastic gradient descent, and it is actually a standard optimization problem that we need to find the parameters to minimize the loss function. Then I used my trained optimized model to predict the value in test set and I compared them with the true values. The predicted values and true values were also plotted together to make the results more intuitive. Okay, next let's take a quick review of the full model. First, LSTM is one of the variants of current neural networks, and it can process sequential data. It is also able to avoid the gradient vanishing and gradient explosion in long sequence data. It is also able to avoid the from the figure, we see the special part of LSTM is that it uses three kinds of gates: the input gates, forgetting gates, and output gate to hold and control the information. Next, we focus on GRU. GRU also has gate mechanism with trained weights. And compared to the LSTM, from the figure, we see that it has less parameters and it lacks of output gate. But it still could solve the gradient vanishing problem because of the gating mechanisms. And making the comparison between GRU and LSTM on this dataset is pretty interesting, and the result is quite surprising, and I'll talk about it later. So next, the transformer has a totally different structure to GRU and LSTM. It was mainly composed by attention mechanism instead of the traditional CNN or RNN. So theoretically, transformer usually has a better accuracy and performance than others, and that is benefit from its structure and its model complexity. So the last we have is XGBoost. It is a very effective implementation of stochastic gradient boosting machine learning algorithm. It is an integration of decision trees algorithms in which new trees can modify the result of existing trees in the model. Okay, then we come to the result part. So for the comparison result, to make the plot more clear, I only use the last 100 data here. So the yellow line is the predicted values, and the blue line is the true values. So I use two different error metrics to evaluate the performance of the model, which is the RMSE and MAE. Because each of the metric has its own advantages, so I use them both for evaluation. Okay, let's see the plasma result first. So from the plot, when using LSTM and GRU, we can see that using gated mechanism models here get a very similar result. So no matter from the plot or from the value of RMSE or MAE, so they both predict the correct trend and period, but the prediction could not fit the peak or the bottom very well. Next, we look the result of XGBoost and transformer. I believe we could directly tell from the plot that they have a better performance than LSTM and GRU. We also have a lower RMSE and MAE than LSTM and GRU. So in plasma, the transformer has the best performance with the lowest MAE, about 23,000. Okay, for the red blood cells result, the performance of LSTM and GRU really make me frustrated. We see from the plot, the yellow line is almost flat, and there's no clear trend or period, and the RMSE and MAE are also very high. The result really surprised me, and even I removed the min-max normalization, the performance still didn't change too much. Luckily, we have the XGBoost and transformer. From this page, we can see the XGBoost and transformer has a pretty good performance, and especially the XGBoost, it only has a MAE around 50. So the transformer also have a fair performance, and it's still better than LSTM and GRU. Here I make a summary of the models and the metrics, and we see the XGBoost win the competition in red blood cells data, and transformer win the competition in plasma data. Okay, to conclude that, in my project, a comparison between LSTM, GRU, transformer, and XGBoost was proposed to make prediction on block data, so that the block centers could make strategies on block storage to avoid block waste. So first, I did the original data was pre-processed, and only the plasma and red blood cells were kept for training. And the data is also scaled into 0-1 by min-max normalization to solve the large scale of the dataset and feature. And then LSTM, GRU, transformer, and XGBoost will all fit into the same data, and the epochs were all set identically as well. Then I used item as the optimizer to minimize the loss function and get the optimized models. The root mean square error RNN and the mean absolute error MAE were used as evaluation metrics, and the comparison were based on the value of RMSE and MAE. And for plasma data, LSTM and GRU has a similar performance, but the transformer has the best performance with the smallest RMSE and MAE. And for the red blood cells data, the performance of LSTM and GRU did not make too much contribution for the prediction. And XGBoost has the best performance with the smallest RMSE and MAE. So also both XGBoost and transformer are effective to reach the peak and the bottom of the data, so that they can predict accurately. So then the transformer and XGBoost could be possibly helpful for block center mixed strategies on block storage. And I believe with the development of current technologies, I believe more powerful tools could be used for blood or medical fields in the future. And that's all my presentation, and thank you for listening.